Good morning, everyone. Sorry. This is Laurent Dubuis. We will wait for one additional minute, and then we will start the diffusion of this webinar. So just a minute, please. Okay, it's now 11 o'clock, Paris time, 10 GMT. Good morning, everybody, and welcome to this second SM webinar. My name is Laurent Dubuis, and I'm a researcher with EDF Research and Development, which is one of the 6 SM partners organizations. After our first webinar on reanalysis in September, we continue today exploring how current climate data and projections can help the energy sector operations and planning. I'm sorry, my presentation is not full screen, which should be the case now. Robert, can you confirm it's okay?
Yes.
It's okay.
Okay, thanks. Just a few words about the SM project. So SM for European Climatic Energy Mixes is a Copernicus Climate Change Services project which develops a proof of concept or demonstrator in close collaboration with the energy sector. And the purpose of the project is globally to enable the energy industry and policymakers to assess how well energy supply will meet demand in Europe over different time horizons, focusing on the role climate has on energy supply and demand. The organization of the project is as follows. It's basically made of 3 technical work packages dealing with the calibration of climate variables, which is work package 2. We have a work package which consists in translating those climate variables into energy variables, let's say demand and power generation from different sources. And this is done at 3 different time scales. So the past, over the last 30 years, seasonal forecasts, which are the next 6 months, and climate projections up to 2050, using different energy mixes scenarios from previous European projects. In addition to this, we of course have case studies linked to a seasonal forecast or climate projections, and we also have a very important work package which is dedicated to the interaction with potential stakeholders. I'm sorry, there is a little bit noise in the background for which I can't do anything, but soon I will give the word to my colleagues. So the agenda today will consist in 2 talks. The first one by Professor Phil Jones from the University of East Anglia in UK. We will talk about present climate data with the interim biases adjustments. And then we will have a second talk by Professor Robert Lothar from CNRS in France. We will talk about the calibration of climate projections and with a particular emphasis on energy applications. Those talks will be 20 minutes each. And then we will have around 15 minutes question and answer session. In your control panel of the GoToWebinar application, you have a questions tab in which you can type your questions on the fly during the talks. I will try to organize those questions, so please specify to whom specifically you would like to ask your question, and so we will take time at the end to answer as much as possible the questions. I'd just like to remember as well that the webinar is organized twice today. So this first session this morning shared by myself, Laurent Dubuis, and the next one this afternoon at 3 p.m. UK time or 4 p.m. Central European time will be chaired by my colleague and friend Alberto Troccoli. Last but not least, the webinar is recorded and it will be made available on our website soon. So I will now give the control to Phil. Yeah, okay. So Phil, you have now the lead, and you can share your screen and start your presentation, please.
Okay, I hope this is working. So I'm going to be talking today about one of the work packages that Laurent mentioned, work package 2, which is looking at historical climate variables relevant to energy. And so much of this talk now will be about historical data. So this is looking at reanalysis and station observations. And there will be something at the end about seasonal forecasts and climate projections, but they are less advanced at the moment in this project, and there will come more in the following year. So what this is going to be about is assessing ERA interim, the reanalysis done by the European Centre from 1979 to 2014, and assessing the quality of that compared to gridded observational data for various variables. And the emphasis here is on the variables that are of greatest relevance to renewable energy. So we look at radiation and wind here, but we're also doing others as well, like temperature, relative humidity, which influences demand, and precipitation, which influences hydroelectric power. They're also relevant. So ERA interim, despite being the best reanalysis available, is not perfect. So we can assess how good it is, where and when, by comparing with gridded observational data or just station data. And by doing that, we can also look at improving ERA interim, and we refer to that as biased adjustments. And as I said, we're also looking at seasonal forecasts and climate projections briefly at the end. So within the project, we've set up a domain, which is showing here, from just to the west of Iceland, almost to about 50 degrees east, and from the north of Norway down to North Africa. So what we do here is to, in order to do this comparison with observational gridded data and station data, we regrid the ERA interim from its grid to a common latitude-longitude spacing at about at half by half degree spacing. ERA interim is available every 6 hours and sometimes 3 hours, depending on the variable. So we have all those aspects in the analysis at those spacings across this whole domain. And so all the data is going to be made available on a website which anyone can access. So you'll be able to access the original ERA interim on this regridded domain, and also the original data as well, and for all the variables. And the reason for doing this regridding is that it's easier to do the comparisons when the grids are the same. ECEM will also develop averages for countries across Europe and also some domains within, or some regions within countries, and there are a number of clusters, 96 of them in total, across Europe from the E-Highway project. So here's the variables we're looking at, the ones that are most relevant for energy. So we're looking at air temperature, precipitation, solar radiation, wind speed, and relative humidity. And in order to look at relative humidity, we need to calculate dew point temperature as well. Relative humidity is not easily available as a simplified variable, and dew point temperature is much easier to work with. Within the project, we're also going to be looking at a few other variables, but we're getting the results from other projects for this. So river discharge and water temperature are potentially important, and also snow cover and snow water equivalent, but they'll be addressed more in the second year of the project. The observational data sets that we'll be comparing ERA interim with is one is a data set called EOBS, which is produced by the Dutch Met Service, and these are gridded fields of daily maximum and minimum air temperature and precipitation on this 0.5 by 0.5 degree grid. And we'll be comparing with some monthly grids that we've developed ourselves in the Climate Research Unit, and also the Global Precipitation Climatology Center of the German Weather Service. But also we want to assess the quality of the wind data and the dew point temperatures, and in order to do that there are not yet gridded products. And so we're using station data from a data set produced by the Hadley Centre of the UK Met Office. This is their sub-daily station data, which goes from the early 1970s through to the near present. So we're accessing that, and it's possible for anyone to access this data as well. And there's wind speed, dew point, and there's air temperature and precipitation as well on that site. Station data across the world's land areas. Then for the solar radiation data, there isn't really a detailed gridded data set available. So we're using here combined data sets from a satellite data set called HelioClim, which was discussed in the earlier webinar by Lucien Wald. And this is also assessed at 55 stations across Europe, where more detailed measurements of solar radiation have been made. So we've had a number of workshops, user workshops within the project, and we've discussed a number of things, and the users are interested in aspects of bias adjustment. And they're interested in whether this bias adjustment introduces more uncertainty, or is it worth doing. So we're having to assess in this project how we might assess the importance of any bias adjustments we do. And we're doing that in another work package that Laurent Debout is leading with energy indicators, so we can assess whether, in terms of more energy specific variables, whether these data sets, once we do the bias adjustment, are improved, or are they the same as they were beforehand. And another aspect that's of relevance is whether we make these adjustments to variables independently of each other. We know in the real world that there's a consistency between variables. When in winter, when it's cold, the air temperature is going to be cold. It might be clear skies, and it's going to be milder temperatures when it's when there's cloud. So we know that there's intervariable consistency, but do we have to adjust the variables accordingly? And a lot of the results from the user feedback have suggested that users are more interested in one or two variables, and therefore at the moment we're less interested in multivariate adjustments, but we are looking into this in more detail in the second year of the project. So the assessment of how good ERA interim is going to look at these gridded observed data, and these are specifically over land areas. So we're not going to be assessing the quality of ERA interim over the North Atlantic or the Mediterranean, simply because we need observational data to assess that quality, and that is mainly collected over land. So there will be some issues if you're interested in wind speeds over, say, the North Sea. There are wind towers which have observational data which can be used to assess the quality of ERA interim, but that is not actually looked at in this particular aspect of the project so far. We have done some work on that, and we hope to report that in a different time during the second year. Now, bias adjustment of the historical period is discussed here, but this also is going to be important for the seasonal forecasts and also for the climate projections. So we will be looking at that more in the second year as well. And the approaches to that are somewhat different, particularly for seasonal forecasts, because of the different nature of those and the ensemble aspect of those. But the potential bias adjustments we're talking at here with historical reanalysis could easily be applied to the projections in the future, and we hope to do that during the second year. Now, a number of bias adjustment schemes have been developed, and one of the simplest ones was developed in the WATCH project and by Whedon et al. In 2011-2014, and they applied this separately to each month of the year, regardless of the time of day. and it was also an independent of other variables. So it's a relatively simple bias adjustment that just looks at the monthly averages. So it doesn't make any difference between warm days or cold days or the distribution of the weather during the month. Now, in this project in ECEM, these daily and sub-daily timescales are potentially important. So, and also potentially the intervariable relationships. So reanalysis incorporates these, but does this individual bias adjustment reduce or alter these intervariable relationships? So we're going to be looking at that more in how the data are used rather than directly in the way we're working at the moment. Now, as I said, there's numerous approaches in the literature and to bias adjustment, and most of this has come from bias adjusting general circulation models and regional climate models. And here the biases are probably much larger compared to observations than they are with reanalysis. And indeed, some procedures actually use reanalysis to bias adjust GCMs and RCMs. A lot of recent methods have gone beyond what Wheaton et al. Did and often referred to things as referred to as quantile mapping or equating the CDFs of the distribution. So what effectively they're doing is they're doing bias adjustment of the distribution of, say, wind speeds measured every 6 hours. So does the reanalysis get the distribution right as opposed to just getting the average right? So we're looking at the whole distribution of wind speeds in a given month. So our approach is similar to these in nature, and we're going to be equating the distributional fits of era interim and the observations based on different distributions for different variables. And this is discussed for wind speeds in this paper here by Tai et al. Now I'll just show you an example of this for wind speed. And the different distributions for other variables are used. So here you've got wind speed is on the Hadley Center ISD data set, so it's station observations, and you can see on the maps the variable station distributions we've got across Europe. A lot of distributions in some countries and less coverage in other countries. But we're going to be using the Weibull distribution, which is commonly used in wind speeds. And you're looking here at how the scale parameter on the left and the shape parameter on the right, how they are fitting compared to the era interim data. So it's the difference between the era interim and the observations. And you can see that on the left for the scale parameter, a lot of the stations are relatively close here to the era interim value. And similarly on the right, in terms of the shape parameter of this distribution, they're also relatively good. But there are differences, and these differences tend to be larger in some parts of Europe, more so in coastline areas and more so in mountainous regions. So effectively what we're going to be doing is, this is the initial test, and if we make our adjustments by taking the shape and scale parameters and then applying those to era interim, we produce results like this, which is on the same scale here, after looking at the adjusted era interim values. So after making our adjustments, we then have a lot more of the stations agreeing, and for both the scale and the shape parameters. But there are still a few where the stations are in maybe odd locations in alpine valleys, or they've got slightly less good data than many other stations. So the fits dramatically improve the results. And we can look at it this way, another way. This is looking at an example for one station, and we have 803 of these stations and plots will be shown in the publications from this work. So here you have for January, February and March here, the wind speed distribution for Kirkwall Airport in the Orkney Islands off the north coast of Scotland. So the observational data, the station data, produce this black line, and the era interim values unadjusted produce the brown line, and then the adjustments we make produce the green line. So you can see the green line is moving the observations moving the era interim values towards the distributional parameters of the observations. So that's just one example. There's obviously hundreds of these plots that can be shown. We're doing similar things also for the other variables, but we use different distributions for them. For air temperature and dew point temperature, we use normal distribution, and for precipitation, we use a gamma distribution. And the publications from this work package will give a lot more of the details. Now, just moving on now finally to radiation. This is done a bit differently from the others, simply because there is less station observations available, good quality station observations, and we're using a satellite data set which is more limited in time than the observational data which go back to beyond 1979 when era interim starts. So if you take an example here for a place in the southwest of England called Cambourne, and you look at the daily radiation from era on the y-axis, and then correlate this with the station radiation measured at the station, you can see that there's a relatively good agreement, but it's not that good. And this is a typical example of somewhere in Western Europe where era interim is not getting the cloudiness right each day, and so the radiation is really dependent on how good the cloudiness is being simulated within the reanalysis system. So we're going to use adjustments to that to make these look a lot better. If I showed a similar plot for somewhere in the southeast of Europe, we got an example from Egypt, where it's normally very clear skies, then this agreement is much better. So the real issue here is making sure that era interim gets the cloudiness right, and then it subsequently gets the radiation correct. So these are the stations that we are looking at where the observations have been made over a long period of time, and we can use these to assess our satellite estimates. So as a result of this estimations, era interim overall slightly overestimates surface radiation. This is slightly more in the more northern regions of the Baltic. There's another different range over say Western Europe, with using France as an example here, and then there's a range for Eastern Europe. And as I said, the bias and this large variation in the errors is simply due to the issues of predicting cloud amounts within era interim. So by making one or two more assumptions, we can calibrate era interim over the period of the satellite data from 2005 to 2014 and develop a regression equation which we can then apply to the whole period from 1979. And this data set has been produced, and then we can assess how good this is by the improvements at these network of stations across Europe. We can also apply this. We're going to going stages further and applying the same type of approaches, but in a slightly different way, to seasonal forecast assessments across Europe. This is only recently finished, and this will be followed up later in the subsequent year in the project. And we will also be looking at climate projections in a similar way to what I've described to you. We can bias adjust these climate projections using these bias adjusted reanalysis. We will do the same variables, and we will be looking at a number of the Cordex regional climate model simulations. And the emphasis is going to be on the daily time scale, which is what's generally available from the Cordex simulations. And we're going to look at a specific one future 30-year period, and that 30-year period will be 2035 to 2064. So in conclusion, we're bias adjusting era interim. We're looking initially at the period 1979 to 2014, but early next year we'll be updating the work to complete the series from 1979 to the end of the current year, 2016. And we'll be later towards the end of next year and maybe early 2018 by suggesting the newer reanalysis called ERA 5, which has been discussed on the Copernicus Climate Change Service website. Now, it is possible, these are all surface observations and variables from ERA interim. We have done some experimentation with wind speeds using their level 58 winds. So these are winds at about 60 to 100 meters above the surface. And this is potentially of use in some of the wind farms over the coastal areas. The seasonal forecasting is going to initially use EuroSIP, but there's going to be improvements made in the near future. And also this will follow through to the direct assessment with our energy variables as well as the direct climate measures. And we'll be doing bias adjustment of the climate projections in the future. So I think my time is up, and I'll finish there. Thank you all.
Well, thank you very much, Phil. You're perfectly on time, which is more than perfect. So we're going to move now to Robert's talk. Okay. So Robert, you should be able to share your screen now and go on for your talk, please.
So, can you see my screen?
Yes, you should move to full screen.
Right.
Yeah, it's fine.
So, is it correctly set up now?
Yeah, perfect.
Okay, so hello everyone. So I would like to first thank the SN team to having invited me. So I'm leading actually another the second Copernicus Climate Change Service project on energy, which is called Clean for Energy, and I would like to thank my colleagues who are listed down there. So I'm going to show I'm going to present very quickly why we do climate projections and how they are made, and also what we can do, some application for the energy sector. So basically, climate projections were made for trying to have a view on how these climatologies evolve with time, especially as a function of the natural and anthropogenic forcing. Natural forcing being solar and volcanic forcing, essentially, and anthropogenic forcing being the change in atmospheric composition of the atmosphere, which is greenhouse gases and aerosols, essentially. So as you see on this figure, which is extracted from the IPCC Working Group 1, which was published in 2013, this we're using global climate projections, which were actually starting much earlier than 1950, but starting more in the 19th century and going even after the 21st century. What these climate projections are made with are essentially scenarios of the evolution of socioeconomics and the emissions of greenhouse gases, and according to these scenarios, we have a well contrasted future, especially at the end of the century. And these projections require a number of other assumptions, which are essentially integrated in the global climate models. The global climate models actually aim at representing all the processes that are within the atmosphere, the ocean, and also the cryosphere, and all the surfaces. So they should account for every process in the atmosphere, also in the ocean, on what we see on the left, which is also in particular, so the ocean variables, which are the of course, the currents, but also the biogeochemical components of the ocean, which are very important for the CO2 sink. And also the changes in the land use and land cover that will occur across the 21st century are also extremely important for the projections. So we are kind of modeling the Earth system with these models. And these models, unfortunately, do not have usually the resolution high enough to be at the scale of the impacts of climate change. So what is done in general is a chain of models, a chain of processing of the data, which goes from the global climate models, which have a resolution of about 1 to a few hundred kilometers, to regional climate models, which are essentially done with the same physics, but with a limited area model and higher resolution, to the impact models. So now the impact models do not talk about the climate variables, but variables which could be variables in the agriculture or here in the energy, the flow stream. And so there is a lot of modeling there, and therefore a lot of uncertainties. The uncertainties from the scenarios, but also the uncertainties from the models themselves and the variability. And that is why we never use now one single model, but we use ensembles of models which are done, which are built from different groups around the world, and we try to do coordinated efforts to have the output data in the same format, to have the same regions, to have ensembles that are consistent over the same grid, etc., etc. So this is typically what has been set up in the last, I would say, decade, which is the CORDEX, which is the coordinated regional downscaling experiment. So there has been a number of regions defined, which are shown on the graph here, and these regions are made for having regional downscaling with higher resolution models. And for almost all of these regions, there is an ensemble of climate projections that have been carried out and assessed in a number of articles that you can read on the different journals at the moment. So these are the CORDEX domain, and I will focus now on Europe. Actually, Europe has a specific, well, the Europe version, which is called EuroCORDEX, has a specific framework because for the first time there was a really an unprecedented range of spatial scale covered by many models, and the higher resolution models are having 12-kilometer resolution. So there is another version with 50-kilometer resolution also. And there is also an unprecedented number of model simulations with a common framework. We all have the same grid, and we use 3 greenhouse gas scenarios, about 10 models in general, and it has been evaluated in a number of papers, and I invite those interested to read all these papers. So just to show an example of what a climate projection is, what we have done here in this figure is to represent on the left the temperature of the summer, the mean summer temperature that is observed around the Paris area, and there's this very famous 2003 heat wave with a very high temperature along the summer. And in the Impact2C project, which was a previous project which ended 1 year ago, we have tried to characterize the climate of Europe under 2 degree or 3 degree warming, global warming. And so this is a typical example of what we can get. On the middle and the right-hand side of the figures, we have these different simulations done from the climate projection models, regional climate projection models. So it looks like a bit like a spaghetti plot, but it is due to the fact that the different models do not, of course, give the same answer each year. But what is important is what we can draw on average. So the result here is that on a 2 degree climate warming, under a 2 degree climate warming, a heat wave such as the 2003 heat wave should still occur, but not so frequently, while on a 3 degree climate it should be almost the average summer. So this is the type of representation, and I would like to invite you to also look at their web atlas. So if you just type, I did mention it in my slide, but if you go to Impact2C web atlas, you will find easily an atlas of the 2 degree and 3 degree climate in Europe. So this is all based on Eurocordex. And what we have done also in Eurocordex and in this project was to try to assess what the changes in wind power load factors could be for European countries for a 2 degree and a 3 degree warming, and assuming current wind farm fleets and other scenarios also. And this is shown, the result is, as an application, is shown in this figure. So what it shows essentially is by country how the load factor, assuming the same wind farm fleets as currently, would change. So it's not much. There's some uncertainty, as you can see, because each model is represented by a sign, and but on average we do find a decrease of the order of a few percent for 2 and a bit more for 3 degrees warming. So there is a general tendency, and it also shows why we need ensembles of models to get really a signal that could be used. If we get only one model, it would still carry a lot of uncertainty. So now in Copernicus Climate Change Service, what we have tried to do is to provide a climate projection data set that would be dedicated to the energy sector. So there is a number of variables. I think Phil mentioned the variables that are used in SM. We have about the same for the climate projections, and actually we are working with SM together. And we have, so this data set is made with 10 models, or 10 GCM, RCM couples, I would like to prefer to say, with also bias adjustment that I will shortly describe, and also a possibility to model subset selection, which was also co-designed with EDF. So the first release of this data set was made on July 2016, and it's a beta test version, so it has no guarantee at the moment. And we are willing to have a second release with also some coordination with ESM reference data, especially on the radiation, because there has been quite substantial amount of work on in SM on the reference data. So I'm just here talking about bias adjustment. So we are not talking about the bias adjustment of ERA INTRIP here. We are talking about the bias adjustment of the climate projections. So we basically use the CDFT method, which is cumulative distribution function transform method, which is a method which was designed a few years ago by my colleagues at IPSL, and it was applied to several variables so far. It has the advantage of, so it's a quantile mapping type of method, but it also takes into account the evolution of climate, in the sense that the transformation from the models of the variable, the shift in the variables, the shift in the distributions are accounted for when bias correcting future data. So this is a method which has also undergone other developments, especially for precipitation, for which we also correct the frequency of precipitation, not only the amplitude. And it's been adapted here to high resolution projections. Actually, the situation is that the climate projections have currently a higher resolution than the observations themselves, so it needs to be adapted, and I'm not going to go in detail for that, but there has been quite a work on that. And so these data are currently available as a beta test, and we are going to release a second version. So we are basing the correction, the bias correction or the bias adjustment on watch forcing. So what we have done was also to compare not the ERA interim but the climate projections as an ensemble with station observations. So I just showed the results for temperature because I won't have the time to do it for other variables such as precipitation. Wind is in the pipe, so we have not finished fully this assessment with station data. And solar radiation is also in the pipe. So what we can see for temperature, it's been compared with 485 stations from the ECA and the data over Europe. So we have some statistics of mean absolute bias, for instance, or biases for the higher and lower quantiles, and we see that we do actually quite substantially increase, improve these biases. The original simulation is rather 2-degree bias on average, and we're having now an average bias for each station of 1 degree or less. So there are other statistics also on the fraction of station with mean bias more than 2 degrees or less. Yeah, so this is of the order of 10% with bias adjustment.
Robert,
Yes?
sorry to interrupt, but you have 5 minutes left. Thank you.
Okay, thanks. So the first applications were done thanks to our colleagues from Météo France, and they were trying to model the future of solar indices. So they are doing also electricity demand and wind power indices. So on the right hand side, what I'm showing is the kind of probability distribution which is smoothed on of the solar power for the UK. So there is a general decrease in this case using these climate projections until 2050 with a significant signal compared to the reference period after about 2010-2020, and this is due to a number of factors, but essentially the increase in water vapor due to climate change, so far as we know. Not all models are showing that. So if you look on the left, these are the different models that were used in this case. And as you see, most models are showing this decrease. But for instance, the CNRM model is not showing such a dramatic decrease, but rather a steady behavior. So it's also important to investigate all models. Then another application of this projection climate data could be to investigate how reference extreme events will have increased or decreased in the current situation or in the future. So this figure shows actually a heat indicator average over French stations, 30 French stations, and it's these are curves of risks. So this is the return period associated with cold spells being lower than the indicator value on the left. So for instance, if you take an event that would, a cold spell of 1 month, that would have an average temperature of about 0 degrees, this would correspond to about an event that would occur every 100 years. So in that case, the blue curve shows the probability in the past from the period from 71 to 2000, and the red curve shows the current situation if we assume that the current climate is the climate between 2001 and 2030. It's we are in 2014, 15. Sorry, 2016, so we are in the middle. So if we add on top of that a reference value of the event, for instance, the cold spell of 1985, we have other cold spells also, we see that the 85 cold spell was corresponding to an event which would occur in the past climate about every 50 years, and that its probability has diminished by a factor of 2. Now it's more than a 100-year event. So it's also interesting to see how these extreme events, which are important for energy, evolve with time. And we can add on top of that some observations which actually fit quite well the model values. And we can add the future. So for the future climate, which is now the 30-year period from 2020 to 2050, what we see is that we have another decrease by a factor of 2 or so of the probability of such an event as the event of 1985, the month of January. So these are some types of application. We are actually developing many more applications of this climate data in the Clean4Energy project for wind power, for electricity demand, for also forest harvesting for biomass, for biofuels, hydrology, and freezing rain, and also applications from climate projections of sea level and waves in the ocean near the coast, near the European coasts. So very quickly, I do not have the time to explain it, but we also have a method for subsampling the models, which has been developed. So if we don't want to take the 10 models or the 11 models that will be available, because we don't have the computer power, we can select only 3, and we have developed a methodology for model selection. In the case of 3, we end up with the models on the right-hand side. And all these data are currently integrated in the international coordinated effort of distribution of data, and which is called the ESGF, for Earth System Grid Federation. So you see on this map all the nodes that distribute the data. currently, and you can go on one of these nodes. So I just showed the IPSL one, but you can go on any of these nodes and have access to all the same data with the same standards. So here's my time is gone. So I would like to thank you for your attention, and please do not hesitate to download the data which are available from our website written below. Thank you.
Okay, thank you very much, Robert. I'm going to take the screen again. It is. I should now share my PowerPoint, and we have quite a lot of questions. So we are 10 minutes to the end of the webinar. As we have quite a lot of questions, as I just mentioned, probably we will go maybe if needed for a few additional minutes. If you're interested to follow the discussion, please stay online. I will ask you, Robert and Phil, to try to answer briefly to the questions, knowing that the attendees will have your email addresses, and I guess you'll be happy to answer more deeply, in more details by email then. But it's interesting to share your answers to those questions. So I will start with you, Phil. Don't forget to unmute your microphone, please.
Yeah, I have done. Yeah.
Yeah, okay. So just I had a question about the presentations. Of course, as I said at the beginning, the webinar is recorded, and both the recording and the presentations will be made available on the DSM website in a few days. So there were specifically two questions for you, Phil. The first one is this one. Are the wind speed adjustments flow dependent on direction and speed?
They're just made on the wind speed. They're independent of direction. So it's just looking at the wind speed measurements, and the domain does include the Moldova.
Okay, so you answered those at the same time, which is very good. Thank you. The two following questions, I think, were for both of you. So the first one is a clarification point. So one attendee asked if the Codex climate projections are intended to be bias adjusted with the ERA interim bias adjusted product.
Yes, and we would also probably regrid the Codex data onto the same grid as that we've been using for the reanalysis as well. So the 0.5 by 0.5 degree grid. We'll be working to looking at a finer grid as well in the project, maybe 0.25 by 0.25.
Okay, thanks.
So one of the issues here is following on this other question. I can see it now. It's to making sure when you're redoing this, when you regrid grids, to make sure you don't lose information, and checking that the same degree of extremes come at the different grid resolutions. So it's particularly important with the extremes, and particularly important for a variable like precipitation. So we are aware that the distributions can be changed by the gridding. So yeah.
I just add another one for you. So while you have microphone, please, can you answer this one as well? So are the adjustments just local or at stations level, or are they done for all grid points of the reanalysis?
They're done for all grid points over the land areas of the whole domain. So there's about 4,500 half-degree grid points on this domain. So the adjustments are done for all of those, for all the variables.
Okay, thanks. Robert, would you like to add something to those two highlighted questions, or?
Yeah, I would maybe just to mention that in our Codex bias corrected or bias adjusted data sets, we have tried to account for the higher resolution, which was quite a challenge actually, by actually bias adjusting at low resolution first, like you did, and then reproducing the model structure within the large within the low resolution cells to still have some high resolution structure, which can be important for orography in particular, in orographic areas. So we have this bias adjustment even at high resolution currently.
Okay, thanks. No, there's specifically, this question, the last one was addressed to both of you. It's about user guidance. So probably you could, each of you could give a response for each project for SM and Clean4Energy, even though I know that the way of doing is pretty much the same. But Phil, would you like to start?
Well, we are producing a paper which will be spitting to a journal soon, and then there are some aspects of reports which are on the ESEM website. So specifically, the best thing here is for someone to email the project or email me or the coordinator Alberto Troccoli to get a specific answer if the question is very detailed. But we're actually trying to provide the information with the data, and that will be available on the website as well as the same place you get the data from it. So we are looking to do that.
Thanks. Robert, would you like to comment for Clean4Energy?
Yes, for the climate projection. So I try to. So maybe there's a question to Phil. This article would only contain description of climate references, ERA interim, or would
yes, it's just related
contain...
to ERA interim bias adjustment at the moment, but we are moving towards the similar work to you with the climate projections. So we need to liaise a bit to make sure we're not doing the same thing, or we're doing things complementary. Yeah.
So this is a wonderful online coordination, because we intend to have also a paper submitted as soon as possible, probably in January or February, on climate projections. So it will be quite complementary, actually. To,
okay, good. Yes. I mean, yeah, we need to liaise. Yeah, we need to liaise in the coming months. Yeah, and we have maybe Laurent can mention this at the end. We have a joint project meeting towards the end of February in Barcelona.
Yeah, we'll come back to this point in the conclusion of the webinar. So Robert, there was one specifically for you. We will address this first, and then we'll take the more political ones, maybe.
Yes, there are political ones.
Yeah. But on the technical side, still, so did you put in the ensemble all the RCMs and after my bias correction, or treated every model separately? And so always the ensemble treated and so on.
So the answer is we treated each model separately, each grid point separately, and even each hour separately. So because it's a bias correction, which is the data set has a 3-hourly time step. So each hour, each month was quantile mapped separately, and we're checking the overall consistency. But let me just add one more thing on the last question, which is on top of the articles, there will be user guidance online also, not as detailed, as scientifically detailed as in the article, but there will be user guidance on the website.
Okay, thanks. And then we online with the selection of models and so on, we just had another one. Was there a selection of models for the ensemble? Or?
So it's a good question. We took actually all the models that could give 3-hourly data. That was our requirement. We had to remove actually one model for which we had problems with data format that was really impossible to handle, but we still intend to improve and add more models. So if the models can provide 3-hourly data, then we include them. So that's the idea. But we have also this selection procedure, which is not based on the availability, but more on the ensemble characteristic of the data. what we have tried to do is to have a sub-selection procedure which would keep the ensemble spread in particular, and would have as also other criteria the quality of model to reproduce the observations, of course, before bias correction.
Yeah, and we'll answer a last technical one, and then we'll try to address shortly the political one. With the original raw datasets, so both for SM and Clean4Energy, so before bias adjustments will be made available as well?
The raw
Yes.
dataset, yes.
Yeah, so okay, yes, in both cases.
Yes.
So I'd like now to come to, yeah, sorry, I kept those for the person who asked those questions, because they are a little bit different. It's more political, so we are rather in a scientific webinar, but it's always interesting to hear about the opinion of scientists on policy. Would you like to shortly comment, both of you, on those questions from a very political aspect?
So, well, I don't want to comment too much, because also this is quite a new setup that we have now. But what I can say about U.S. policy, we don't know what will be really the U.S. policy at the moment. But what we know is that there is currently a very large development and deployment of renewables in the U.S. And also it also depends not only on the federal state, but also on the federal government, but also on the states. So even if there is some strong political move, there will still be a strong trend to go to less carbonized energies. So, but this is, I cannot go much further than that.
Okay, Phil, would you like to add a comment?
Not really, no. I mean, we'd have to just wait and see, really. There's too much in the media at the moment about what the US is or is not going to do. So we'll just have to wait and see.
Yeah, I fully agree that we are not doing science on Twitter, and we should wait for concrete achievements and so on. Okay, thank you. So we are now getting at the end of this webinar. Before closing, I'd like to advertise two events which are closely linked with today's topic. The first one is the joint symposium between the two Copernicus energy projects, so SM and Clean4Energy. This symposium will be held in Barcelona on the 22nd and 23rd of February next year. So details and registrations can be found on both projects' websites. The second event is the fourth edition of the International Conference Energy and Meteorology, so ICEM 2017, which will be held in the south of Italy, in the wonderful Bari region, on 27th, 29th of June, with a pre-conference seminar on the 26th. Once again, the registration is not yet open, but the call for abstract has been issued. The deadline is the 27th of January, and this year there's something new, because we created a Young Scientist Award, which will consist in a full registration, full free registration for the winner. Sorry, I have an issue with my presentation. It should not be the case, but yeah. Okay, no, it's okay. So I would like to thank you very much for your attendance and for your time this morning, and especially I would like to thank Phil Jones and Robert Botta for the presentations and the involvement in that. We will stay in touch for our website in the coming days. As I said, the presentations and the recording will be made available. You can stay in touch to be informed about our next webinars. There will be other ones next year. And you can also follow us on with our Twitter accounts on the WENSI website, the WENSI being the World Energy and Meteorology Council, which is also part in the organization of this webinar. I'd like to thank you again, everyone, for your participation this morning, and wish you a very good day. Bye-bye.
Okay, thanks, Laurent.
Okay, bye, Laurent.